So this time we are going to talk about controller design. So PI controller design for DC motor control. DC motor control. Okay. Now, primarily, we have a couple of parameters that are associated with a DC motor that we will want to control. We have torque that we would like to control, which is one of the variables that, when you interact with the mechanical system, you want to be able to control torque that you apply. The other option is, or other variable is controlling speed. Okay, so we'll look at both of them and look at what we need to do to design a controller, primarily a PI controller, a proportional and integral controller for a DC motor. Of course, you might want to do a servo control loop too, and if you do want to implement a servo control, then we'll have to look at the precision signal as well. But primarily, this discussion will be on developing either a current loop or a speed loop or a cascaded configuration. Okay. Now, for current and speed, a PI controller will be sufficient in most cases in applications that you see very common. Now, and the approach that I'm going to show you here is not the only approach that you are going to see. There are other strategies, especially when you look at it from a control systems perspective. There are certain analysis you can do, but this is a quick and dirty method that you can easily set up a controller with very good, very reasonable control and reasonable performance. Okay, and you'll have the control, the ability to choose bandwidth for your controller. Okay, now before we go and start doing the design, I want to make sure we are on the same page in terms of what we call bandwidth. Okay, we will come across a couple of different responses when we are looking at the frequency domain. If you look at a first order response, that in frequency domain as a Bode plot, the magnitude plot, right? We look at omega versus the magnitude, let's say in dB. Okay, and if you look at this system, you will have 0 dB, and then you see a drop off like that. Okay, and then we know, at least if you remember, this negative 3 dB, this is the negative 3 dB point. This we call the cutoff frequency if you are looking at it as a first order low pass filter, right? Now for this kind of a response, we typically call this to be the bandwidth, omega bandwidth. Okay, now one difference that you will see is when you look at practical systems, depending on the type of system, you may not have this gain of 1 or 0 dB at the low frequency side. Sometimes, either due to the actual system functionality or due to certain characteristics, you will see a slight decay of gain. Okay, and you may have seen this in your advanced circuits classes, electronic circuits classes, where your response is more or less like this. Okay, if you recall from ECE 358 at SVSU, you might remember that for such cases, you typically choose this as your bandwidth. Now, there's no harm in choosing this full scale if this region is very small. If it's a very tight band of frequency, you are welcome. I mean, you can, without much influence, you can choose this as the bandwidth for your system. Now, it's one thing us choosing that, it's another thing how the system will operate in this region. So that those are two different things. Primarily, we look at the operation, or we'll focus on the operation in that range. And for a first order system, if this is due to measurement error, then it will still operate in the low frequency side. And for a motor, more or less, it's going to look like that low pass filter response at the low frequency. And so it's going to be flat up here. Okay, so just so that we know what bandwidth is. From the electronic circuits, bandwidth tends to be slightly different. Right? Okay. Now we're gonna look at the DC motor system. First of all, we will look at designing a controller for the current loop. Okay, if you remember, let's try to draw them out. I'll try to draw this as as much as I can. So we have our back EMF. If you remember, now we're drawing the system as a block diagram. As a block diagram. Okay. Okay. And then we have KT. Right? And then this is our electromagnetic torque. CEM. This is my load. EL. And then this passes through my inertia and damping. And then we have omega R. Okay. Now, if we are performing a current loop, if we have a current loop, this is where our controller is going to be at. And then we have our current error. Right here. We have our current loop, right? We are measuring current because this is our current coming out of the system. This is our electrical system. Call this C1 of S. This is our first controller. And then we have a second controller. This is the cascaded control system. This is our C, well, we'll call this CI of S. We'll call this CS of S, S being speed. Okay. To the speed controller, you will have a speed reference, and then you have a speed measurement all the way from here. Okay, and then if you want, so now you can see that this is our current measurement, IA star, right? And this is our IA, our armature current, right? So the speed controller sets the current reference, and then the current reference works in this works with this controller to set the current. Typically, the inner loop is faster. When you would like to be it to be faster because you want the dynamics in the inner loop to settle before the out loop kicks in. Otherwise, the outer loop will try to correct every time because the inner loop is not changing as fast enough. And you can do all sorts of control system analysis from the point of view of a control system and see and understand that stability. But I'm not going to try to do that here. And the second thing is rate limitation. For example, since the speed controller is setting the current reference, we need to set some kind of a rate limit or a maximum current reference. So you can use some of these saturation blocks. I don't know if you have seen this. There are some saturation blocks in MATLAB. They're basically clipping your current command at a certain value, because we don't want to set the current reference beyond the capability of the motor. Because if we do, it'll still try to reach that current in order to meet the command from the speed reference. Okay, so you can set that limiter block in between the voltage controller and the current reference, in between these two. Okay, so it goes right around here. So that otherwise in the simulation it's okay. Not having this is fine, but in practice you might go into a very large current command, and then your battery voltage might drop, and that could induce other issues into your system. Okay, so first of all, we will look at this. How can we design this to meet a certain criteria? And then once we have that set up, we'll assume, okay, this is a very fast responsive system. That means IA star is IA. And with that, now this kind of disappears. So it becomes just a line. And now we can analyze this larger system or the outer loop to design our controller. Now, another practice that people follow is the feed-forward control. Feed-forward control loop basically comes in right here. So you have your reference changing, right? So depending on information you have about your system, now you can actually influence, rather than letting the dynamics or the commands pass through the closed loop, you can directly influence the applied voltage based on the information you have about the speed. For example, we know that if we command higher speed, you are going to need more voltage, right? So based on the feed forward information, the currents that we have, we can set or drive this voltage a little bit higher so that the burden on the closed loop system is reduced. Okay, this is one common practice, and then you can follow different strategies on what you are seeing in the system. If you have a lot more variation on omega reference, you can develop certain strategies to respond to certain frequencies and not respond to certain variations. So there are a lot of research studies have been conducted in that area. Okay, so kind of one topic that you might come across. We are not going to go over the feed forward path just yet. Okay, so this is kind of the problem we're going to tackle first. Okay, now so let's take a closer look at the current loop. Current loop. Okay, let's try to draw this part out. So we have plus, minus, T, and we have the controller here. Okay, so since you said we are okay with just using a PI controller, so I'll show you how to do that design. So let's say we have a KPI. I'm going to use I for current plus So this is Ki I. So now don't get yourself confused with the integrator. So the first letter means whether it's a proportional or integrator. I means it's for current. Okay, this is very useful when you code stuff up, when you write your program, to distinguish which gain is corresponding to what controller or which controller. So you have your back EMF here. Now we're trying to design a controller in this case. Now, before we do the design, we have to now think, okay, we have here, we have one pole, right? We have one pole. This is the first order system. And here we have what? What do we have? We have one pole in the denominator and 1 0. Okay, so the approach that we are going to follow is I'll show you how to design KP and KI so that we can do a pole zero cancellation by and set the desired bandwidth. It's going to be a very elegant method. Now, before we do that, we have a little bit of a roadblock. We have our back EMF interfering and we don't know how to handle it just yet, right? So what we'll do is we'll treat back EMF as a disturbance. Okay, since this is a linear system, right? This is a linear system. This is a summation or the subtraction. It's a linear system. When you assume based on superposition, we can actually omit the disturbance, get rid of that back EMF term, and then we can design our controller and then add the disturbance back in, and the response will be it won't have any effect within a certain criteria of operation. And yes, Michael, yeah, so we did look at a similar method for EC461, but this is going to be purely from the point of view from choosing bandwidth, or how we can incorporate bandwidth. And in 461 we looked at, okay, what are the control variables we'll have? We have gain as well as bandwidth, and here we'll only focus on just selecting bandwidth. Okay, all right. So now in order to achieve that, I'm going to propose now, before I draw that system down here, I'm going to say my KP of I, this is going to be RA times omega bandwidth of the current controller. Okay, let me make sure that's, yeah, so this is for the KP, and RA, this is 2 pi F bandwidth I. Okay, so just converting it to hertz. All right, now depending on your system bandwidth and what you want the ultimate closed loop bandwidth to look like, you can set these values. Okay, in doing so, you do need to think about your sampling frequency, your delays that you could encounter in the system, and then how much energy, how much voltage you have, because if you demand higher bandwidth, your controller is going to try and inject more and more voltage to drive the motor. So you have to be very careful. Okay, so it depends on what system you have. For simulation purposes, you can try anything. Okay, you should be able to reach any bandwidth given you have sufficient sampling frequency. And then for Ki of I, I'm going to say we'll choose LA, the inductance, times omega bandwidth comma I. It is the same bandwidth. Note that. Okay, it is the same bandwidth. All right. So now with this, let's redraw our system, and here I'm only showing the forward path. and let's redraw with our back EMF assumed 0, and with the closed loop we'll see what we have. Okay, so let's see. We have here what do we have? We have RA omega bandwidth I. If you take S, we have an S here, plus LA omega bandwidth I over S, right? Very nice. And then this went to 0, so we don't need the summation anymore. And then we have 1 over RA plus SLA. And then we are only taking a current measurement, so we don't need to worry about our KT. So that's what we have, right? So this is our IA star. This is our IA. Okay, guys, see what? What are we? Why are we focusing on controlling the bandwidth? Like, what does bandwidth matter? Okay, so good question. Now, bandwidth is basically your response time. Okay, because when we are designing a controller, we need to know how fast that controller is going to respond. For example, you have a torque actuator, and if you can design your torque actuation to have a response in the seconds time scale, or you can design it to have milliseconds time scale. Okay, so let's say if it's a steering system, do you want it to have, you know, a 5-second response, or would you rather have 500 microsecond response? If yeah, which one do we prefer? If it takes 5 seconds to respond, right? Probably we missed the exit. You're trying to turn, right? Exactly. Okay. So let's go here now. See, this is the relationship between the bandwidth and the cutoff. See the relationship bandwidth and the cutoff, right? So frequency. Oh. Okay. Good question. All right. Now that's it. So why we care about, right? Care about omega c. Now for a first order system, what do we know about tau? So let's take this guy, right? What is our tau? What is our time constant? Okay, so here in this case, RA over LA, right? Now, how is RA? Can you guys recall anything how RA over LA or tau is related to our cutoff frequency omega? You guys, do you recall this? How is the time constant related to our cutoff frequency or omega cutoff, which is in turn going to be related to our bandwidth, right? How is tau related to our cutoff? Anyone remember? It's way back, in the beginning of 460. . Michael, you might remember this a little bit better because we kind of hammered on this in 461.
Yeah, I'm thinking.
Well, now 1 over tau, right? 1 over tau is your cutoff frequency, right? Okay, so now by setting your bandwidth, you're basically choosing your cutoff frequency,
I think I
and
remember.
yep, yeah, exactly. So,
It's just a
but
poll, isn't it?
exactly, that's your pole, right? So by choosing your cutoff frequency, you have selected by increasing cutoff frequency, you are selecting your time constant to be faster, right? So if your time constant is faster in the real world, the time it takes to respond to a step input is going to be shorter and shorter. So your system is more and more responsive just for that command. Okay, so if you want to make the system faster or respond faster, you want to have a higher bandwidth. Does that, Garrett, does that make sense why we want to have a higher bandwidth? Okay, now you have to be very careful. So this is, this is a balance that we have to strike when you do a system design, right? You don't want to have very high of a bandwidth because now you're going to have noise influencing your system. So you might see unintended actuation, some vibration passing through the system if you have too much bandwidth. So always you have to make sure you are reasonably, you're selecting your bandwidth in a reasonable manner. Okay, and what the cool thing is, now with this configuration, now we can actually change the plant characteristics. You'll see what will happen. Okay, now here what I'm going to do is I'm going to simplify this a little bit more so that it kind of highlights the point I'm trying to show. Okay, again, there are different methods, different approaches to take. This is a quick and dirty method to design your PI controller if you know your plant characteristics, at least reasonably close. Okay, so what we can do is we have our bandwidth, right? That's common to both, and then we have our S term. So let's take that term outside. Okay, that's omega bandwidth comma I over S. We just took it outside. It's a separate block. And then now when we look at what's left over, what we have is RAS plus LA over 1. And this is from our controller, right? And then in our plant, we still have our 1 over RA plus, oh, wait, did I mess something up? RAS, I think I did, didn't I? Yeah, so, okay, let me, actually, when you choose KP, this is LA. Let me correct that. This is gonna be LA. This is RA, okay? LA. Otherwise, it won't cancel out that transfer function. Okay. So here, I'm gonna cross this out and let me update this diagram too. This is LA, this is RA. Okay. So now, okay, now this might be a little bit better. Okay. So we have our omega bandwidth comma I over S. Then we have RA times SLA, right? Because RA times SLA over 1. And then from our plant, we have 1 over RA plus SLA. Oops. And then we have our IA star here, right? So now very nicely and very conveniently, we are able to cancel the pole from the controller 0. Okay, so this is IA. And now we only have as a transfer function is this term. Okay, so if I ask you to find out or derive or come up with this relationship, the transfer function between IA and IA star, what is that going to be? That's going to be forward path transfer function over 1 plus the forward path times the feedback path gain, right? So in this case, if it's 1, we're going to be left with omega bandwidth I over S over 1 plus omega bandwidth I over S. So this becomes omega bandwidth I. We can take common denominator and cancel out S. S plus omega bandwidth I. Okay. So with this, and I hope you guys remember this. Now, if we take this omega bandwidth out, we're gonna get 1 over S over omega bandwidth I plus 1. Okay, a very nice first order response, which the cutoff frequency is based on the bandwidth that we selected. Okay, so if let's say we look at our system, right? So this is in dB, this is in omega. Our original motor may have been a system like that. Now by selecting bandwidth, you can either move it slightly ahead, or you can even retract it. I don't know why you would want to do that, but you could retract it slightly back. I mean, not slightly, but theoretically speaking, you can move it as much as you want, but you have to be very careful when you do that. Okay, so now we have actually changed the cutoff frequency, and it will behave the way we want it to behave. Okay, do you have any questions on what we just did? Yeah, so I recommend you guys to try this in your Simulink. You know, you can build a motor model, you can build a simple controller, see how it looks like, and now you can even test it with different speed variations. Your controller will still perform because your back EMF is going to be still there in your motor model, right? Still, the current loop dynamics will treat the back EMF as a disturbance, and it'll try to adapt based on the variations you have, and it'll still perform like we expected it to perform. Okay, good. Now, so I think we have a really cool setup here, but few things that we need to keep in mind. When we design our controller, we rely on, so our KP, right? Our KPI is basically LA omega bandwidth I, right? KI is RA omega bandwidth I. Now, your KP and KI are calculated based on your motor parameters, right? So that means you need to have your parameters to a reasonable accuracy. That's one thing. We need to have our parameters to a reasonable accuracy. Two, if for some reason your parameters change, or by mistake you use the wrong parameters, now you create a second order system. Okay, so that's something that you have to be careful of, because second order systems have a resonance frequency. Right? So a slight variation, you don't see much issue, and even with a second order system, uh, it it might work fairly okay depending on the characteristics. But just be careful, if you change them that much, it could have a big impact on the overall system. I mean, so is for any other type of controller. Okay, so just keep that in mind when you design such a controller. Oh, no. They are so very easy to calculate or measure. Well, we did the lab, remember? RA is your armature resistance. LA is your armature inductance. Right? You can remember the locked rotor test that we did for the DC motor lab. Uh, that was giving us easy. Well, datasheet, if you buy a motor with a datasheet, most likely they will have a nominal value, because motor production, it's a mass motor production. So they're made in, large numbers, and they cannot, in general, they cannot say this motor has this resistance, this inductance, right? So what they do is they take a whole batch, they'll find the distribution, and then they'll give you a mean value. They'll say, okay, this is your mean RA value for this batch, and they'll issue one data sheet for that. Okay, so there's certain margin of error in that value. As long as that spread is not too much, the variance is not too large, you can use this method to design a controller. In applications where you know exactly your resistance and inductance, it might work even better. Okay, but if need be, you guys know how to measure inductance and resistance of a DC motor, right? The step response, you apply the DC voltage and you look at the step response. From steady state voltage, you can obtain the resistance. From time constant, you can obtain the inductance using the resistance, right? It depends on the application, Garrett. So if you are looking at a system where you need to focus on accuracy and you need precise actuation, servo, very precise operations or functions, you might want to use the actual resistance and inductance. But if you are okay with some variation, you can use the datasheet value, or kind of the nominal value of the resistance and inductance. I've seen both ends, and I've even seen applications where certain algorithms try to real-time measure parameters. Yeah, large-scale safety-critical applications. So one thing they try to do is they try to minimize variation. So you have two things, right? You have two ends, actually. You can either have a large variation and measure accurately, or you can design for minimal variation from machine to machine, so minimal parameter variation. So if you can follow a design practice with precision to achieve that, less than 5% variation or less than 2% parameter variation, now that means your system will, using the nominal value, will have less adverse effect or less performance degradation. So for I can't particularly comment on EPS because this is going to go up on YouTube, but kind of trying to explain the two ends that they follow. Okay. Maybe we can talk about it after. All right. Okay. So we talked about the current controller. Now let's go into our speed controller and then see how we can choose or design our speed controller. Okay. It's going to be very similar. Yes, correct. You can type in. Okay. I'll keep talking. Now, let's go back to our original diagram here, right? So we basically designed our control loop, our closed loop system for the to control current, right? So when we do that, now we have a very nice control here for that loop. Okay, and then for the lock rotor case, if we set our back EMF to 0, then what can we say about IA, the reference, and IA? Yes, Garrett. Let's talk about that at the end. Okay, I can explain a little bit more about that manufacturing many motors, and we can talk about that. Okay. So looking at this speed controller design, all right, if we have a fast responsive current loop, right, which means we have fast dynamics here, we design the bandwidth to be a very high bandwidth current controller, and our plan is to design a low bandwidth or relatively low bandwidth speed controller. Okay, so that means the speed control loop is executing slower than the torque control loop. Okay, when we do that, what can we say about the dynamics within the current loop compared to the speed loop? Can we comment on the dynamics of the current loop with respect to speed loop if the speed loop is slower? So if our speed loop is, if we design that slower, right? Yes, Levi, what do you think? Is it, what do you think? What can we say about the dynamics of current? And we kind of talked about this when we talked about the different poles in the current loop. Not really. Current loop is responding very fast, right? So actually, remember, now we figured out a way to control bandwidth, right? So naturally, in general, we can say the speed control loop or the mechanical system is going to be slower. That's true. But we could design it to be slower or faster, right? Now, if we design our current loop to be faster, we can assume that the current dynamics have settled. They are responding fast enough that at an instant this dynamic loop disappears. So this has come to a steady state way faster than the speed loop. Therefore, IA star is equal to IA. So we actually don't even see the effect of this inner loop. Okay, because it's responding so fast, we don't even see that. Okay, so in order to design our speed loop, we'll use that, and we'll consider the back EMF 0. We'll still treat the back EMF as a disturbance just until we design the controller. Okay, so let me stop this. All right, so now let's see what we have here. So if you assume our IA star is equal to IA, so this this becomes just a straight line, right? So then we're going to be left with, so this is our speed loop, right? And then we'll have another controller here, KP, what did you call that? KPS plus KIS over S. And then output of that is what? It's going to be current, right? And current times KT. It's going to be, so this is going to be electromagnetic torque, and that minus the load torque is the differential torque that goes into our 1 over JS plus B, right? And then this is our motor speed. Now we can actually we have our feedback loop, right? So if you remember in our 460, when we did the speed controller lab, we characterized our system as a first order system. If you guys remember that, right? For whom you have taken 460, and this is what we exactly did. Instead of coming up with these values theoretically, we experimentally measured the transfer function. Okay, so very similar approach here. All right. Okay, so now we have our TL, our load torque. Similar to our back EMF, we can treat load torque as a disturbance. We can assume that to be 0. Okay, so then we are left with the following system. We're going to have the controller, we'll have KT, we have 1 over JS plus B, right? So we have a very convenient system now that we can design our controller. Okay, so for this case, so KPS for the speed controller, we can choose our gains in this way. We can say J over KT, because we have a KT term here, right? Times omega bandwidth S. Okay, for Ki of S, we have B over KT times omega bandwidth S. Okay, so we have this. Now let's see what we get once we design our controller. Okay, of course, like before, we'll kind of simplify this to begin with. We have a common term, omega bandwidth right? Omega bandwidth S, and then we have 1 over S. So we can take that out. Bandwidth, come on, S, if we can factor that term out. We are left with, I'm going to make it a little bit different here. So here we have what? From KP we have J. Is that, it should be J? Yeah, it should be J. Yes, so JS plus from KI we have B, and we have 1 over KT, right? However, we have a gain of KT, so this gain is going to cancel that out, and then we have our mechanical system JS plus B. The 0 will cancel the pole out, and what do we have? We have another first order system, right? So now here, if this is our omega star and this is our omega, omega over omega star can be written as omega bandwidth of speed over S 1 plus omega bandwidth over S. So this becomes 1 over S over omega bandwidth of S plus 1. Right? Very nicely, we have another first order response. Now we can take these and cascade in our original system. So now we designed our KPI, the current controller. We designed our speed controller. Now you can cascade them together in this final complete system, and you can apply step responses. You can see how your system responds. Okay, so a very simple, very nice approach to design your controller gains without going into a lot of stability analysis. The primary reason that we can do that for a DC motor is because it's a first order system, both electrical and the mechanical independently, and that's actually because it's a first order system. We can easily cancel the pole out and design a simple PI controller to achieve the control operation that we expect. Okay, same goes for here. If you change your inertia, if you change your damping ratio, let's say you change your fan design for a speed controller, now your controller, the function is not going to operate as you expected. Okay, so it'll have a second order response, and then behavior might be different from what it used to be. So you have to recharacterize if you change that, if you change those physical or underlying system characteristics. Good. What do you guys think? Does that give you a good idea of designing your controller? Your poles are going to be stable. Your controller poles, they're going to be stable. We do have a 0 there, right? So you can study dynamics, you can look at the root locus, you can look at the stability, the bandwidth, all that based on this system design. Okay. Now, one thing I want to recommend to you is take some data. Maybe you can choose RA. I'll give you RA. RA, assume 0.1 ohms. LA 250 microhenry, and a KE of 0.0006 volts per radians per second. Okay, so for a simple motor like this, right, you can now design a current controller. Okay, and if I give you J, let me see, 4.25 times 10 to the negative 5. I forget units for this. Yeah, I don't want to lie here. But SI units, this is SI units. I forget units for the J. And for B, I believe this is 0.0027. Okay, I think this is, what is this actually? Yeah, I might have to look up these units, but yeah, for J and B, given this, can you design control loop and try to simulate that? See if your responses are acceptable, right? And then try it without this limiting function and with the limiting function. What does it do to the system? Because having this current limiter will make your system nonlinear. Okay, so that's why we design it without the limiter and then we add that later. Okay, so one exercise you can try is, simulate that. Feel free to share your results with me, and we can even discuss them in detail. Okay, good.